No, you did not just walk into a music class at Georgia Tech. This is actually antenna engineering. You're at the right place. But I thought we'd start today by talking a little bit about acoustics because it's the perfect introduction to standing waves on thin wires. The violin, of course, just has a different kind of standing wave on a thin wire. The math turns out to be the same. So we always start all of our lectures in antenna engineering with show and tell, pieces of antennas and circuits. It just happens to be a musical instrument nowadays for today's lecture. Somewhere in Italy, in a gravesite, the body of the composer Boccherini is probably spinning around after that performance. But I do promise that we will end the lecture on some real talent. Okay, so we're going to start today with a discussion on current standing waves on wire. That's our first topic. It's labeled ANT01 in the online notes. It's the very first topic in a series of discussions on wire antennas. So, to continue with our musical theme, let's go ahead and take a look at this video online. Hopefully this will play through the recorder capture here. There's no sound to this. This is straight off of YouTube. What it is a slow motion picture of a bow with a hard grind on the G string of this violin here. So for those of you unfamiliar, this is G, this is tuned to D, this is A, and this is E. These four strings right here, E, A, D, and G. And if you're really into music, this is technically the third octave G, the fourth octave D, the fourth octave A, and the fifth octave E. And if you are an extraordinary AV nerd, G3 corresponds to a frequency of 196.0 hertz. And D4, if you please, is 293.7 hertz. A4 is 440 hertz. And finally the E5, that really thin string at the top, 659.3 hertz. Now, by now you've noticed how the string is vibrating there on that violin. You can see a standing wave forming as that rosined bow grabs the string and starts to dump vibrational energy into it. And what's interesting about this is that the bow itself is very much a white noise source. It's capable of putting any kind of acoustic energy of any frequency onto a string. Look at that, even after it's lifted, there's a resonance, a persistent standing wave vibrating back and forth on that G string. Now, you might be surprised to learn that this, like so much in life, can be modeled with circuit theory. So let's go ahead and figure out how to do that. How do you model a violin with circuit theory? Well, you start, like everything, with the transmission line. this transmission line, it's supposed to be Z equals D units long, where Z equals to 0 corresponds to the spot at the front of the line here. And if mechanical displacement is like an electrical current, then the violin is best represented as an open-circuited transmission line resonator, or at least the individual strings on it are. Now, why is that? Well, what happens at the end of a transmission line? If there is a wave traveling on here, when that wave gets to the end of the transmission line, the current has to go to 0. And that's not unlike a violin string. If I look at the side of a violin, I've got the neck and the scroll with all the tuning pegs over here, and then the body of the instrument is down here. The bridge represents a point where the string cannot move. It's fixed on the bridge because it's bearing down with quite a bit of pressure. And likewise, there's a little bar up here on the neck called the nut, where also the string is pinned down from pressure and kept from moving. The string is free to vibrate, at least to some degree, anywhere in between here, but it cannot have any mechanical displacement here at the ends. And so that's not unlike current on an open circuit transmission line. The current, of course, has to go to 0 because there's no load connected to this. And if both ends are open circuited, then it turns out that only integer multiples of the half a wavelength will be supported in this transmission line. What do I mean by that? Well, let's take a look at voltage on the transmission line. Voltage does not go to 0 at the end of the line. If you have a standing wave, it'll actually reach a maximum at an open circuit. Because, if you remember your formulas from class, the reflection coefficient gamma for an open circuit is +1. 100% of the waveform is reflected because it has nowhere to go. The energy cannot dump into anything, and it's a +1, meaning that there's no phase change. But that's actually for voltage, keep in mind. Voltage. For current, the current is always doing the opposite reflection polarity of what the voltage is doing. So, if I'll switch, you'll permit me to switch to multimedia colors here. Let's do our current waveform in blue, and then our voltage waveform in green. So if I look at the current on this transmission line, I have a current waveform that's traveling, got the polarity of that one wrong, traveling down the line like this. There's a current waveform going this way and a current waveform going this way, and they're superimposing on one another. By necessity, the end has to be 0, and this end has to be 0, and there's going to be some sort of standing wave. Now, it turns out that in order to have constructive interference, that is, the wave comes down here, reflects back, hits this end over here, reflects back, and if it is to be in phase with the wave that started the whole process, then this length has to be a resonant d equals lambda over 2, half a wavelength. Why is that? Because going down a half a wavelength changes the phase of the wave 180 degrees. There's a -1 reflection coefficient for the current waveform, so that means I've changed 180 degrees by traveling down the end of the line. The phase change at the end is another 180 degrees. I now travel the other direction. I have to travel another 180 degrees. And when I get to that end, it reflects back with a -1 reflection coefficient for a total of 180 degrees. The net modulus 360-degree change when all that happens is 0, meaning that when the wave completes one full cycle around this resonant structure, it's back in phase with itself, which means you have resonance. If I change that length, I make it a little bit greater than one wavelength or a little bit less than one wavelength, I get complete destructive interference when I have successive reflections again and again and again through the structure. So only this resonant lambda over 2 times some sort of integer length can support this type of wave. And the fundamental, of course, occurs in both acoustics and electromagnetics when an n is equal to 1. That's the dominant mode that's going to form here. So, in modeling my violin circuit, what I find is that bow, we said, is kind of like a white noise source. V sub n as a function of time. And you'll notice that in a violin, of course, the bow doesn't actually happen exactly at the end or even in the middle of the string. It's kind of offset. In a way, providing a good impedance match at this particular junction for a resonant transmission line that is lambda over 2. Now, when we're studying standing waves, we have to recognize that this is what the current is doing. What the voltage is doing is something different. It still obeys the exact same resonance. But the standing wave is not a hump of current with minimum at the end. It's actually an inflection where you get maxima at the end. So if I were to drag a voltmeter across here, I might get a total peak here that goes through an inflection point and then gets to the opposite peak as I drag my voltmeter over here and I measure a voltage that is basically a mirror image reflected on what's going on the other side. All the while, the current waveforms on the top and the bottom bar are adding together to form that waveform. So, the violin string behaves most similarly to an open circuited transmission line when viewed with respect to current. I could just as well make the analogy to voltage with the acoustic deformation on a string or displacement on a string. In that case, I would probably want to use a transmission line with short circuits on both sides to represent the fact that there was 0 volts being enforced as a boundary condition on that transmission line, forcing the current to be, or the voltage to be 0 at the ends and a maximum in the middle for the fundamental. It's all an analogy. It's all just math in the end. So we can construct our analogy however you want. If you like to work with voltage, you can work with voltage. If you like to work with currents, you can make the analogy with currents. We're going to stick with the current analogy because ultimately we're going to talk about currents on wire antennas. And if we can guess what those currents are, which it turns out that you can for a lot of simple type of wire antennas, then you can predict what the radiation is going to be. Antennas, in general, behave as three types of problems. The first type of problem is you know the current and you need to solve the radiation. This is actually what most engineering professors start teaching their class when they teach antenna engineering, and this is going to be no different in this class. In this case, the second case, which we'll get to later in the class, if you don't exactly know what the current is, but you kind of know what the field distribution is in front of the antenna. And it turns out there's a class of antennas that this works really well for as well. For number one, wire antennas of all sorts of shapes and sizes can be solved this way. For number two, things like horn antennas, parabolic dish reflectors, where if you actually had to solve for the current on these big complicated structures, you would drive yourself crazy. But they're constructed in a way to make the field in front of them relatively predictable. And if you know what that field is in front of it, you can use sort of what I like to call the grown-up version of Huygens principle, which in this class we call the Kirchhoff-Helmholtz integral theorem, to project how that structure radiates into the far field. And so if you know the field distribution, then you can solve for the radiation. The most general class of problems in antenna engineering, however, are numerical-based problems where you neither know the field around the antenna or the current on the antenna. Because in a way, those are chicken and the egg problems. You need special cases to help you out to figure out one or the other without being able to solve for both of them. For numerical techniques, the most general class of antenna engineering problems, you're given a piece of metal, maybe an excitation point, some arbitrary shape, and you need to figure out its electrical properties and how it radiates into space. That's a very challenging problem because, as I said, it's a chicken and the egg problem. How do you know what the currents are on that antenna without understanding what the fields around it are? But those fields around it cannot be solved unless you figure out what the currents are on that antenna. So this kind of raises a conundrum. And it's a solvable, tractable problem in electromagnetics, but you have to resort to something called integral equations. And that's a fancy word. It doesn't mean equations that you have to integrate. Georgia Tech students have no problem doing that. That wouldn't be an issue at all, if only it were so easy. What usually that means is that the thing that you're solving for is underneath a multidimensional integral. For example, solving for the current on an arbitrary metallic structure. That current is under an integral that you have to enforce boundary conditions on, which makes it very challenging. So, violins as antenna circuits. Let's just take this. Well, first of all, let's do a little bit of review. Now, hopefully, you've reviewed some of the content that we recommended. Time harmonic transmission lines 01, Phasor review. This will help get familiar with my terminology that I use. And 02 is helpful as well. It's basically introduction to time harmonic transmission lines. And then wave 01, Maxwell's equations. It's going to be helpful later on. We're going to get to that in a moment in this class. And then wave 02, the Helmholtz wave equation. this will give you quite a bit to chew on. And we'll get you familiar with the terminology and the notation that I use in my classes. There's sort of this joke among electrical engineering EMAG professors. If you lock 15 academic professors in electromagnetics into a room and ask them to come up with a standard notation for presenting their courses or their material or writing their papers, they will leave the room with no fewer than 16 different notation schemes. So these will at least help you get familiar with the way that I like to track things and write things on the board or the screen, as is the case. So let's talk about the Phasor solution to the transmission line formulas here. Okay, so let's go ahead and write down the full solution in Phasor form for that transmission line of length D. Now, what does this look like? Okay, voltage as a function of Z equals to 0 is over here, Z equals to D is over here. That's going to look like some sort of amplitude in general, V plus, and there is a forward propagating term, exp to the minus j beta z. Beta is, of course, 2 pi over the wavelength. And if there's a forward propagating wave, this is a simple linear device, there should also be the ability for a backwards propagating wave to be sent. That's going to have amplitude V minus, and it's going to have this same exponential taper. It's just going to be in the opposite direction. As usual, I'm running out of room. That should be plus j beta z. Let me give myself a little bit more room for the current solution, which has the exact same form. Current as a function of z. And keep in mind there's always a top bar and a bottom bar current, right? And they're always symmetrical on a transmission line, opposite. That's not to be confused with the forward current waveform and the backward propagating current waveform, which superimpose at any point to give two oppositely polarized identical currents, which are represented by this phasor. Of course, we know it's a phasor because there's a little squiggle on the top of it, and that's the convention that we use in this class. This waveform is going to have the same amplitude as the forward propagating voltage, but you're going to need to divide by the impedance of the line in ohms. Every transmission line has a intrinsic impedance in ohms, square root of the per unit length inductance over the per unit length capacitance. If you remember your undergraduate junior level EMAG class. And it has the same exponential propagating term with a minus in front of it. The minus is characteristic of forward propagation in the positive z direction. And there's a big difference. There is a minus instead of a plus sign. And then you have v minus over z naught. And we flip the sign. It's always good to go back and try to confirm what these means, positive and negative exponential linear phase tapers. In the phasor domain, they always mean forward and then backwards propagation in the minus z direction. Because if you think about it, your phase should be rewinding as you advance forward at any given snapshot in time, which is why this is linear with respect to z and has a minus sign in front of it. Again, beta 2 pi over lambda. And there's some other constitutive relationships that you have to follow here too. there is a velocity of propagation on the transmission line. If you remember your formula from undergraduate EMAG, it's always 1 over the square root of the per unit length inductance and the per unit length capacitance of the line. And Vp should always be equal to the wavelength times the frequency. And of course, this is true for our violin string as well. So we'll do an acoustic example when we're done all of our standing wave math to calculate, see if we can translate the frequency of notes and the length of a violin string into a velocity of propagation on that string. Okay, so let's continue on in this math. Now we went up here, we said that we have the voltage and the current solutions, but really there are some simplifications we can make. Let's get a little space here. First of all, for the voltage waveform, we said on a transmission line with 2 open circuits on either end, we're going to have the exact same V plus amplitude as the forward and the backwards propagating wave, which means what we're left with is minus j beta z and plus exp to the plus j beta z and I'm just going to go ahead and divide this by 2 for no good reason, and I'm going to put a 2 out here as well. Why would I do such a thing? Because most of you talented students that have taken some advanced math classes recognize this is going to be Euler's definition of cosine. And boy, that looks so much nicer than that expression that I had earlier. Just an amplitude times 2 times cosine beta z. Remember what cosine looks like if it starts out positive over here at z equals to 0. If I go, in this case, lambda over 2, just like we said, I'm going to go pass through the inflection point to get to lambda over 2. And look at that. I'm exactly negative, just as we predicted for our voltage waveform in resonance on that half wavelength transmission line. That's what the standing wave looks like. However, I said that it was current standing waves that were more important for antenna engineering at this stage in your life. And so let's do the same thing. Here we're going to have both V plus over Z naught is going to be the amplitude of both forward and backwards propagating waves. And I'm going to have those exact same two terms, exp to the minus j beta z. Remember, I have a minus sign here, but I also have the same amplitude waveform going backwards. There we go. So I'm getting used to my stylus here. I got a Wacom pad this summer to test it out. Took 2 extra months to come in on the mail because I think everybody ordered one of these things. Every teacher that wanted to try their hand at online learning or online teaching. Okay, so here we go. Divide by, for no apparent reason, 2j. which means I got to put a 2J up here. And the savvy student would recognize this as sine beta Z. So, my final solution for my current standing wave is going to be, in fact, what I need here is actually a minus, because I would like to put minuses there, which means I'm going to have J2 V over Z naught with a minus sign in front of it and a simple sine beta Z. If we graph this on the waveform, sine of 0 is equals 0 is going to be 0. It's going to hit a maximum halfway down the line, and when I get to Z equals to lambda over 2, I get a beautiful null there, and that's my standing wave for the fundamental on either a transmission line or, if this were mechanical displacement, a violin string. So let's do a quick fun calculation here. I went ahead and measured my violin. Between the nut and the bridge, the 2 points that make contact, that's 0.330 meters. We said that has to be equal to lambda over 2. So if I wanted to look at the E string, that's the really skinny one at the top with the high pitch, that would imply that lambda is actually equal to 0.660 meters, or about 66 centimeters. And if we take the E string of the violin, we said in the beginning of the lecture that that was 659.3 hertz. Now I know that velocity of propagation has to be equal to 659.3 hertz, the frequency, times the wavelength. Let's keep it in SI units, 0.66 meters. Of course, hertz is 1 over second, 0.66 meters. That gives me a result of 435 meters per second, which is how fast a vibration travels down the E string of a violin. Okay, couple questions. How does that compare to, say, the speed of sound in air? Is that even a realistic number? Let's take a look. If I look it up on Wikipedia, I find speed of sound in air is 343 meters per second. Pretty quick. So it's actually traveling faster than the speed of sound in air. And that makes sense. Acoustic waves often travel faster in solids than they do in fluids. That's not a surprise. This is a good sanity check, in fact. At least we're getting something in the range of the order of the ballpark. Now, how do you change the velocity of propagation of a string? This is actually very important for constructing a violin or tuning it, as is the case. One way is to simply make the string heavier and bulkier with a thicker cross section. That's why the G string is at a low pitch, the D string is a little bit smaller, the A string is smaller still, and that E string is fairly tight, very small. There's less to vibrate, so the wave can travel faster, not surprising. The other way, of course, is to adjust the tension of the string. And that is the pull on it. The tauter it is, the faster that wave will travel, which is why you have basically coarse tuners on one end of a violin and fine tuners on the other, and you use both to try to hone in on the right tension that gives you the precise tone. And if the violin is toned up properly and tuned to these magical strings, then you'll get some beautiful resonances if you play it properly. And if it's untuned, you don't want to listen. So 435 meters per second for a string. If we wanted to model it, we said we could use a white noise source. It's located somewhere, maybe, I don't know, 5/6 of the way down the transmission line, which is our violin string. And this is a wonderfully frequency selective system for generating a tone when you're putting in something that is really just garbled white noise with respect to time. However, you still have to turn it into music and send it out into the world. And to do that, if we wanted to take our modeling to a ridiculous extreme, we would notice that the bridge transduces much of its energy into a cavity resonator. And one way to model the bridge is as a simple capacitor. It keeps this looking kind of like an open circuit to maintain the resonance, but does allow some energy to transduce into a cavity where it resonates back and forth. Now, if you've studied cavity resonators in one of our previous classes, we'll actually study them a little bit in antenna engineering, maybe 2/3 of the way through the class, when we start talking about horn antennas and waveguides. But a cavity resonator, the kind that we teach in 4350, especially to start out, is just a big metal box. You put a hole in it, and you put a feed, you excite an electromagnetic wave, it resonates back and forth and back and forth, and not unlike the string, there is a resonant fundamental mode that if you're a little bit above or a little bit below, you can excite it. We'll only excite that fundamental frequency. Because it's not a simple TEM, transverse electromagnetic structure, like a transmission line is, a cavity resonator has lots of different modes. The fundamental, or the cutoff, is the lowest possible frequency that it can excite. As we learned in classes, a rectangular waveguide with the ends sealed up is a nice rectangular cavity resonator. It has very predictable modes that you can excite as the frequency goes up for a particular geometrical structure. The bigger the structure, the more modes it has, the bigger with respect to a wavelength. You'll always hear us be talking about that in antenna engineering for the rest of the course. We talk about size, we talk about electromagnetic size, not the absolute size in terms of meters. It's all relative to a wavelength. So we have that cavity resonator. We excite it. And maybe if you cut some holes in the cavity resonator, some of the electromagnetic energy would eventually leak out into the air, not unlike the F-holes of a violin that allow a lot of the sound to escape the instrument and for an audience to appreciate it. So, the interesting thing about cavity resonators, though, is that if you look at their frequency responses, they do ideally have these discrete modes that get excited. And the positioning of these modes is very much a function of the shape. And what you learn in cavity resonator theory, or just about any other type of resonator theory, is that the lossiness of the resonator determines how actually thick these peaks are. In the ideal one that we first introduce in our undergraduate classes at Georgia Tech, those metallic electromagnetic RF resonators are ideal. So we model these as impulses. You physically cannot excite any other frequency of mode or sustain any propagation inside the device in between these discrete peaks. But of course that's only true if you have a superconductor cavity resonator. Every other cavity resonator on Earth has some sort of loss associated with it, which means that these are not really impulses, they're kind of a little bit broader. They have skirts to them. The lossier the cavity resonator is, the wider each mode is. So what's interesting is that the cavity of a violin is not unlike the cavity of a cavity resonator that we use in electromagnetics. One difference is the shape. The shape of a violin is much more peculiar and more complicated, curvier than a metallic waveguide. And what's more, we actually want it to be a little lossier than your typical metallic waveguide, because we want people to be able to hear the music inside of it. And that's good. The complicated shape that a violin takes ensures that you have a big number of dense, irregularly spaced modes all through the audible range of the instruments. And there's enough loss here so that these all blend together. So ultimately what you have with the violin is some sort of cavity resonator that can be excited at just about any mode within a certain frequency and project the sound outward. So my apologies to all the musicians in the audience. This has probably just drained the life of a beautiful artistic passion that you had. Now you can go home and try to model your flute or your saxophone or your bass or whatever as a transmission line resonator, and you'll never see your instrument the same again. So thank you very much for joining me, and I hope to see you back here in antenna lecture number 2, which would be antennas and circuits. Now that we understand transmission lines, we've done our review, we understand what a standing wave looks like, we're going to take it to the next level, talk about standing waves on wire antennas. And how does that look from a circuit perspective? And then after that, that's when the course starts to get real fun, because we're going to have to start diving into some vector calculus to figure out how some radiation modes work. So let's go ahead and end the lecture with some genuine talent here. This is Itzhak Perlman, one of the greatest living violinists of all time, and we'll end watching him play Gavotte and Rondo by Johann Sebastian Bach. A gavotte is a 4/4 piece in which the beat is felt on the third note, and this piece is considered one of Bach's many masterpieces. He wrote a lot of stuff for violin. Lots of it's famous, but this is maybe one of the most famous ones. I think it was even included on that golden record that they put on the Voyager spacecraft. So let's go ahead and finish out with someone that actually has real musical talent.
Bach, Gavotte.